Good afternoon, everybody. I hope everyone's having a wonderful day. So today, as the title might suggest, and what we've just said, this talk is going to be very much about algorithms. Now, I'm a theoretical computer scientist. I'm very fascinated by algorithms and the resources algorithms require to solve problems. So for those that aren't acquainted, recall that, so for those that do, but for the purposes of this talk, often when we want to solve problems, we think about each problem as a set of problem instances. So you can think of each one of these problem instances as something I could feed in terms of inputs to an algorithm. And the algorithm gives output. Now, the thing that I would like to have is that for every one of the problem instances that my algorithm produces correct output. This would be the solution to the problem. Now, one natural thing is, okay, so that's nice. That's nice. So what do you mean by problem? So in this talk, we're going to talk about optimization problems. So let me talk a little bit about what that means. So you can think of a problem as a set of instances. Those black dots, for example, I have on the screen. We're going to be focusing on optimization problems. So for every one of my instances, I would like to design or discover an algorithm such that every single time I get a solution that follows the constraints of the problem. We call these feasible solutions. And the goal in an optimization problem, depending on how we formulate it, we're going to see an example in a moment, is how exactly, well, first, what is the algorithm? And two, what exactly are we looking for solutions? So for an optimization problem, you can imagine I get you some output that is a feasible solution. It follows the constraints of the problem. Imagine I could pick it up and I could inspect it. So from that, I can evaluate the value of that solution. We call this the objective value or the value solution, the solution's value. So in an optimization problem, we have a goal for which we want to minimize. In our case, we're looking at minimization problems for this talk. It saves me a lot of time talking. Otherwise, I talk about minimization and maximization. It makes things a lot more convoluted. For minimization, the goal is to get it so that every single time my algorithm outputs a feasible solution. So like in my picture here, I have these blue dots. So for every one of the instances, I have a set of feasible solutions. I want the ones that are in that circle that are labeled optimal solutions. So that's typically what we would like to get when we want to solve optimization problems. But it's not just that. I want to come up with efficient algorithms that are capable of doing this. But there's a bit of a problem from a complexity theory standpoint, is that many problems have efficient algorithms that we know about. There are many, many others that we don't know how to efficiently solve them. And in fact, there's even problems out there that I don't even know, like you could actually prove that there is no such algorithm that can even solve them. So what I want to focus in on are problems that we don't necessarily know how to solve efficiently. So tangentially related to this talk, because I do need to bring this up, is today is Pi Day. And I like to think of a day like this as a celebration of mathematics more broadly, and think about numbers, not just pi, because pi as a phenomenon in physical systems and mathematics and so on, occurs, and it's very fascinating when it does occur. But I want to show you in my talk that otherwise mundane numbers, like pi, can pop up all over the place and have earth-shattering consequences for complexity theory, which could turn our entire understanding of complexity theory on its head in otherwise strange circumstances. So one tangentially related topic to this talk is P versus NP. Now, I'm not going to talk about P versus NP in this talk. What all you need to know is for this problem, which is one of the millennium problems, if you go to Clay Math, you can find a description of this problem. For this problem, there are two possible outcomes. Either there's so-called P is equal to NP, or P is not equal to NP. Now, many computer scientists believe that P is not equal to NP, but it doesn't necessarily have to be the case. This problem is an open mathematical problem. It's one of the most notorious or infamous of all problems in computer science and among the mathematical sciences. So what I'm going to do in this talk is I'm going to talk about things in the context if we lived in a universe where this so-called P is not equal to NP. So I'll talk a little bit more as we go through the talk what that might mean for us. So our goal is to come up with efficient algorithms that solve optimization problems. But if we live in this universe, it's possible that it will be the case that some problems just don't have efficient algorithms for solving optimization problems. So what exactly does that mean for us? How are we going to reconcile the fact that there could be intractable problems? These are problems we don't have efficient algorithms for yet, or they may not even exist in the world of p is not equal to np. Some problems will have it where there's no such efficient algorithm in the fray that we've been talking about in a provable guarantee way. So the question is, okay, how do we reconcile this? So a lot of people have all sorts of different answers to this. So for example, thinking about heuristics, thinking about using AI or machine learning and things like that. Some other people are like me, where I sit around and I think about problems very deeply and prove theorems about them. So it's a whole bunch of different ways of approaching these things. So I would like to be able to tell you that problems can be solved with mathematical certainty. Now, I would like to have it where I can have it so the algorithm, and I like to think of this common phrase. I'd like to think about it, it's very down to earth about trade-offs. There's this phrase called fast, cheap, and reliable, pick any two. You may have heard about this when you deal with anything in life, like buying a car or anything like this. And the thing is, if for some problems, if we live in one where p is not equal to np, you will not be able to achieve all three of these at the exact same time for a problem. So for example, I may not be able to come up with fast algorithms for a problem. Or if I want a fast algorithm, I have to sacrifice the quality of the answers. Maybe I have to adopt some heuristic. Now, I don't have to. This is actually one of the main points of this talk, is that you don't have to sacrifice it for just every old day experimental approaches. You can actually sit down and actually mathematically prove the guarantees of how close the answers actually are to the optimal. And of course, we want reliability with our algorithms. That means for every one of the problem instances, like in my picture here, for every instance, the algorithm produces output. And this output, what I'm going to do is I'm going to tell you that we're going to minimally reduce the cheap aspect of these three quantities. I want to try to get it so that I get an efficient algorithm. For us in computer science, we often think about it for intractable problems as polynomial-time. And I would like to have it so that whenever I get a feasible solution, if I measure how good that answer is, it's always going to be within some closeness to the optimal. So it's going to be a multiplicative factor. It's going to be how close you are to the optimal answer. So you might ask, Dan, what does this have to do with pi and all these other things you told me? Well, we're going to get there. So I got to define what an approximation algorithm is. So there's a lot of stuff here on this slide that I just feel like I need to point out. Is first, there's the value of the solution, which that's what alg-I is in my definition here. Opt-I is the value of the optimal. So a k-approximation algorithm in our definition here is going to be that the algorithm that I have on the board over here, this algorithm here always has to run in polynomial time in the worst case. So it means for those that aren't acquainted with this terminology, it means that the number of operations that the algorithm always will produce for a given size, input size always has to be no more than a polynomial number of operations with respect to that input. So the other constraint is that, like I said, I want to have some guarantee of how close the answers are to the optimal. So it's always going to be that it's always going to be k times the optimum at most. So that means I have a nice bound of telling me how close I am by a multiplicative factor. So that's what an approximation algorithm is. So for example, if I told you I had a 2 approximation algorithm, that means that the algorithm always produces answers that are no worse than twice as bad as the optimal answer. So we call this k the approximation ratio, and the intuition behind it is that I would like to make k as close to 1 as possible, because if I give you a 1 approximation, that would simply mean that the algorithm always produces the optimal answer, right? So for these problems that we know of that are very difficult to solve inside of this class called NP, we have these things we call NP complete problems. We have an optimization version for each one of, or at least many of these, we call NP hard. And I'm going to be focusing on these NP hard problems that I've that are optimization problems in this talk. What are these? These are simply problems at this stage that we do not know how to solve in polynomial time in an exact way. That means that in our definition, that would mean the approximation ratio is equal to 1. So the idea here is I would like to make k as small as possible. Now I must stress that I can always make k a function, for example, which for very difficult problems that may actually be something I have to deal with. So I thought I would give an example just to tie everything together so everybody understands what an approximation algorithm is, because I want to make sure you walk out of this talk knowing at least one algorithm. So I'm going to talk about multiprocessor scheduling. So some people call this make-span minimization on identical parallel machines. And it's denoted in the scheduling theoretic literature as PCMax. So here's the idea. So I have a set of jobs, so I have n of those. I have m parallel machines. Now for those that aren't acquainted with parallel machines, you can think of it as an agent that processes tasks, but each one of these machines operates independent of each other. And as soon as one job finishes, the next job can be immediately processed. So you might ask, okay, so what about these jobs? Well, they don't have any order they're required to be placed on. It's a very classic problem, and each job has a length. So for example, if I place a job onto, say, one machine, and say its length is 3, that means it takes 3 time units to execute that job in the schedule. So here's the idea. I need to produce a schedule, so a feasible solution is a schedule, and it has to contain every job that I've been provided. It has to assign each job to exactly one machine. And I must stress that in this setting, for those that are kind of more CS-oriented, we're talking about non-preemptive scheduling here. That means that as soon as in my schedule, as soon as a job starts, I can't pause it or migrate it to another processor or think about it as another machine. Sorry, I'm getting very excited here just talking about this. So imagine if I wanted to talk about, okay, so what does that mean non-preemptive? It just means as soon as the job starts, I can't stop it until it's completed. So you can think of these as vital tasks, for example, for a computing system. Or you can think of it more classically. You can think of it as just a bunch of people with some tasks they need to get done, and they have to work as a team. So the goal here is to minimize the length of the schedule. We call this, in scheduling theory, the make span. So I must stress that unless p is equal to np, so in the world that if p is not equal to np, that means that there is no efficient exact algorithms for this problem that always compute the optimal answers. So the only other consequence of this is that unless we sit in this one where I can actually do it, which we believe we don't, at least in the premise of this talk, we got to think about what we could do as a consequence. Well, we could design heuristics, we could do all sorts of stuff. I'm going to show you that with approximation algorithms, you can actually come up with some really fast and simple algorithms. So just to give you an idea what the problem is, just to really hammer this in. So if I were to talk about this example here, I have 5 jobs. I've represented their lengths by their horizontal widths, and I want to place each job onto a machine. And this is a representation of so-called a Gantt chart. So I have 3 machines, I have 5 jobs. I'm going to place each one of the jobs on a machine. So just as an example, here's a feasible solution. So for example, I've assigned job 4 and job 5 to machine 1. And for example, job 1 is placed onto machine 3. So you might ask, can we do any better here? And the answer, of course, is yes. Notice that job 2, I can easily slide job 2 down into be assigned at machine 3, improving the overall make span from 5 down to 3. So the question is, okay, so that's great. One thing I do want to note here is that if you actually sum up over all the processing times or all my job lengths here, this actually exactly equals the average load. So you can think of make span minimization in this context like load balancing. So that's one thing I want you to keep in the back of your mind when we're thinking about this. So I'm going to show you our first algorithm here. So this is a classic in approximation algorithms and operations research, is list scheduling. Now this was first analyzed by the great late mathematician Ronald Graham, and it's effectively this. It's a very simple rule. So all I'm going to do is I'm going to schedule the next available task on a machine with least load. That's it. So believe it or not, for those that are more CS oriented in the audience, you can actually pick up a lot of things that you may learn in a course like CS340, like a third-year algorithms class. You could pick up a lot of the things that we did over there, and you could actually implement an algorithm that uses the list scheduling rule, and you could actually just use a priority queue, and you could achieve, for those that are interested, it's big O of n log m running times if you just design an algorithm that just repeatedly does this to each job. So, plain language, all we're going to do is place each one of the jobs onto a machine with least load, the one that's the least busy. So, what does that mean for us? Well, here's an example. So suppose I have the 5 jobs again. So I'm just going to place the first 3 jobs. Notice that I'm not going to care about what order they're in. This is a feature of the algorithm. It doesn't matter what order I schedule the jobs. It's just that I could take them in any order. I'm just going to read them off from left to right. So I'm going to place job 1, job 2, and job 3 on machine 1, machine 2, and machine 3. Each one is a machine with least load. So job 4 is going to naturally go on machine 1 because that is the one with least load at that time. Now, one thing I want you to take note of is this line I've drawn. This red line. Notice that this line at that time on my Gantt chart that represents the time horizontally, notice that every machine is busy doing something to that red line or earlier. So it means that none of them are idling by just doing nothing. They're not just lounging back like they're in a lounge chair waiting for the next task. So just keep that in mind. It's an important observation. So when I put in the 5th one, notice the same idea. The red line just moves to wherever the machine with least loads time would be when I place the last or most recent job. So you might ask, Dan, how this seems really simple. Like you said that like this multiprocessor scheduling problem, this NP hard problem, doesn't have efficient exact algorithms. Well, I'm going to show you that approximation algorithms give you a completely different way of looking at complexity. So here's the idea. So I could take that line and I could think of it like one rectangle. So I'm going to think about how we're going to figure out this approximation ratio. So I'll tell you up front, we're going to get a 2 approximation. So there's 2 things I want you to notice. So let's head over here. So you'll notice that I schedule a whole bunch of jobs, right? I have a whole bunch of jobs that go on these machines. And then I have some job. Say, I'll just keep putting some more jobs on here. Suppose I consider a job that finishes last in the schedule. So I suppose that I call its machine ML. So this is the machine that finishes last, and it dictates the make span. So the question is, how long is the schedule? So there's 2 nice lower bounds that if I studied this problem, I can obtain. The first thing I should tell you up front is that this job can't be too much longer than the optimal make span, right? Because the jobs all have to be in the schedule, right? And each one has a length. So that means right up front, if I give you any one job, PJ, well, if I look at the longest job and I call that its length P max, most certainly it has to be that that's no longer than the optimal make span, right? Right? Because it has to be in the schedule. Likewise, another one, I don't have time to derive it for you, but most certainly you could get an intuition based on the first example I gave you where you notice how all the loads, if I'm able to perfectly cut up the jobs, I'm able to cram them all such that it meets the average load or the average sum over all of them, all of the jobs. So another nice lower bound that I have is that I can consider all the jobs. And if I consider this is the average load of a machine when I have all the jobs, this is actually also at most the value of the optimal make span. So I'm going to use these 2 lower bounds on the optimal solution such that I'm able to tell you that it's going to be no worse than 2 times as bad as the optimal make span. So you might ask, okay, so what's happening here? So when I schedule this last task on that machine that finishes last, notice I had the red line, right? So let me just get to the full screen here. There we go. So suppose that I have my last task on machine ML. Well, all of this, there's exactly M machines, right? There's exactly M machines in my schedule. And up to this point, I'm going to call this TL. So everything up to this point, this will be TL time units in my schedule. So you can think of this like an area of a rectangle, but let's write out what the make span would be at most. So if I think about alg I as the value of the solution for my instance, well, this can be no more than TL plus the maximum length of a job. But we already established that the longest length of a job can be no more than the optimal make span, right? So you know right away that this is going to be at most opt. But what about TL? Well, this is where it gets interesting. Notice that everywhere inside of this box I drew, all of the machines are busy. Based on that observation, you'll notice that if I wanted to sum up all the processing over all of the machines, all I end up getting is this follows. So all I have to do now is I just simply say, okay, well, what is that? That's M times TL, which you know this has to contain at least all of the jobs. So most certainly it's at least going to be, so it's going to be bounded by the sum of all the jobs. But here's the thing, divide by M on both sides. So you're going to end up with TL is at most the sum over all the jobs, which this, remember, it's 1 over M times that because I divide by I divide by M on both sides. And now this is the average load, which is at most opt. But what is that? Well, this means that this is at most opt. So for those that are in the audience, I need to ask your question. So if I were to write some number here times the value of the optimum, what should go in this box? Can you say it loud for me? Yeah, 2, exactly. So this is actually the hand-wavy way, less elegant write-up of how you could actually prove that list scheduling is a 2 approximation algorithm. Is that neat? So you might naturally ask, Dan, where are you going with this? So let's talk about this. So first thing I need to point out is that there are better approximations for PC Max. In fact, if you just simply sorted the jobs, because notice I was completely oblivious about the order of the jobs I took them in. If you sort it from longest to shortest, the approximation ratio, I'm not going to prove it here, but it actually goes down to 4/3 instead of being 2. So you can just sort the jobs from longest to shortest. This is what we call longest processing time. If you do that, you could drastically improve the approximation ratio. But you could go even further than that. There exist these things we call polynomial-time approximation schemes for this problem. So here's how I like to think about it. You imagine you have a dial or a knob. And for each tick on that knob, you're able to select a value for a constant we're going to refer to, and it's not really a constant, but it makes it easier for me to explain. I could have a constant called epsilon. And for each epsilon, what if I told you that there's some way to come up with a 1 plus epsilon approximation algorithm? And that's what a PTOS provides, a polynomial-time approximation scheme. So you can think of it like a knob that I can turn. I can make it closer and closer to 1 if I like to, and I could get actually answers as close as 1% close to the optimal in polynomial time. So believe it or not, if you take a more approximate view of these things, a problem that otherwise somebody would tell you is NP hard is actually fairly easy to approximate. But here's the intuition that's sort of the trade-off here. If you think of epsilon not as just something that you decide on in advance, you think of it as something that varies, that you get to think of it as varying with the running time. It may be possible that as epsilon gets closer and closer to 0, the algorithm gets slower and slower and slower. That's the trade-off. So we think about it as if you were to fix the epsilon, that means it runs in polynomial time. But if you think of it as a variable, most certainly it doesn't behave exactly like that. There's all sorts of things we could say about PTOSes. But the point here is, do all problems have PTOSes? So that's the first thing I want to address. And let me get to that. So I'm going to first assess a generalization of PC Max. So the first problem we just talked about, I'm going to impose an extra constraint on the problem. Now I'm going to say, hey, look, now you actually have to impose an ordering on the job so that one job has to finish before another one can start. This is what we call precedence constraints in scheduling. And a very natural way to represent these is as a directed acyclic graph, or a DAG. So for those that aren't familiar with DAGs, just simply think of it as I have all those dots there. The vertices are nodes, they represent the jobs. And if there's a directed edge that goes from a job to another job, that means that the first job has to be finished in its processing before the next job can begin in the schedule. It doesn't say where it has to, it just says the order in which they have to be processed. For example, job 1 has to finish before I can start doing job 4, for example. Likewise, I can't just simply start job 3. I have to wait until job 2 and job 5 are indeed finished in the schedule. So you might ask, okay, so what can we do there? Now here's the neat thing. You can actually use the same list scheduling rule that I talked about to come up with a 2 approximation algorithm there, and the proof is fairly similar to the one I kind of outlined for you. Now you might ask, Dan, is there a PTOS for this? And unfortunately the answer is no. So you might ask, okay, so how good can you do? That's a very natural question. And here's the answer, is that it is actually a lot more complicated than just saying, do PTOSs exist or they not? And most certainly, it's problem by problem. And here's the thing. What complexity theorists and theoretical computer scientists tend to get very fascinated by is what's the best possible thing you can do unless something happens. So this is very common with the idea of a reduction, which I don't have time to talk about here. But most certainly the idea is if I were to find a better approximation algorithm with an improved approximation ratio, how good can it be? So here's the idea. I'm going to imagine so first I have my friend here. So you know how I talked about I have a 2 approximation algorithm? Well, I could tell my friend, hey, look, there's a 2 approximation algorithm for identical parallel machine scheduling with precedence constraints. It's like, yay, that's wonderful, because that's an NP-hard problem. Well, I would like to tell my friend that, hey, look, you might ask, okay, how good can we do? So I'm going to put a pin in the ground, and I'm going to tell you, if my friend over here tries to cross past this pin, it's going to cause all sorts of weird stuff to happen. So that's the idea here, is that there's some theorems you can prove, and this is based in an area called hardness of approximation, is that we use complexity theoretic assumptions to prove if you can come up with a better approximation algorithm. So if I have my friend over here, I can tell them, hey, look, you can't cross past this pin unless P is equal to NP, which if many computer scientists don't believe that P is equal to NP, for example. Keep in mind it's an open problem, but we just don't know. We just have a lot of evidence one way or the other. So we can think of these numbers like magic numbers in programming. Some people in programming might tell you, oh, magic number is just some hard-coded constant I use. It works. It's the same idea when you think about approximation algorithms in this context, is you might say, okay, so how good can you do? Well, the unfortunate thing is that you will have to reconcile if P is not equal to MP with these constants that exist that otherwise are mundane numbers. And they manifest themselves in different problems, just like the constant pi does in many physical phenomena. So in this case, the magic number is 4/3. If you come up with an approximation algorithm with an approximation ratio less than 4/3, then you actually can provide me a proof to show me that P is equal to NP, and you'd be solving one of the greatest problems in all of mathematics and computer science, and you'd be famous forever. So this is what we like to do. So you might ask, okay, can we do any better there? So keep in mind, this is something I proved, right? But I don't have a 4/3 approximation algorithm yet for this problem. There is no such thing yet. So a lot of people study, okay, can we do any better than this? So a natural question is, okay, so can we prove better theorems? And that's really a big open question, because it either we're too silly and too stupid to come up with a better approximation algorithm, so we can tell our friend to come closer to the pin, or it's just that we lack the theorems to say the pin's actually over here. And it's really unclear sometimes. So I want to give some quick examples before I stop here. So just 2 things. So first, you may know of things like the traveling salesman problem. The traveling salesman problem, you won't be able to find such a magic number because, in fact, you cannot come up with, say, for example, a 100 approximation algorithm for TSP. You can't do it. It actually provides you a way of testing if a graph has a Hamiltonian cycle or not in polynomial time. Likewise, you can actually think about persistent gaps such as unrelated parallel machine scheduling, which the magic number there is 1.5, and scheduling theorists still don't know how to resolve the best known approximation ratio, which is 2, versus this 1.5. So researchers such as myself have been thinking about this. So for example, we studied a problem called graph balancing. And in this case, we're able to come up with a 3/2 approximation algorithm for this special case, where we think of the scheduling problem as a graph, in particular a multigraph, and we orient the edges. So sometimes you can actually reach the gap, but it tells you ultimately a phenomenon. Is it that the problem is just that by specializing it like I've done here, is it that it's just that it's easier, or is it fundamental to unrelated scheduling in this example? But anyways, I'm going to stop right here. I want to say thank you very much, and have yourself a beautiful day.